voltage follower, direct coupled voltage follower. So this is the circuit diagram of direct coupled voltage follower. The output terminal is connected directly to the inverting input terminal. The signal is applied to the non-inverting input and the load is directly coupled to the output. In a voltage follower circuit, the output terminal is directly connected to the inverting input terminal. As the input voltage changes, the output follows the input to keep the inverting input terminal voltage equal to the non-inverting terminal voltage. So this is a basic op-amp circuit connected as a voltage follower. When the input voltage at terminal 3 is increased or decreased, the feedback effect causes the output to follow the input almost perfectly. The voltage follower has a high input impedance, a low output impedance, and a voltage gain of 1. The typical difference between input and output voltage with a voltage follower is only 5 microvolt when the input amplitude is 1 volt. Next, capacitor coupled voltage follower. When a voltage follower is to have capacitor coupled input and output terminals, the non-inverting input must be grounded via a resistor R1. Non-inverting terminal grounded via a resistor to provide a path for input bias current. It also offers an input resistance to the signal source rather than a short circuit. The DC offset voltage at the op-amp output terminal can limit the amplitude of the AC output voltage. So a resistor R2 equal to R1 should be included in series with the inverting input terminal to equalize the IB/RB voltage drops and thus minimize output offset voltage. The circuit impedance is Zin equal to R1. The capacitance C2 you can obtain from this expression XC2 equal to Z0 plus RL at F1. F1 is the lower cutoff frequency. Likewise, capacitor C1 you can calculate from XC1 equal to R1 plus RS divided by 10 at F1, F1 being the lower cutoff frequency. Next, inverter. The following diagram shows the inverting configuration with the 3 inputs VA, VB and VC, depending on the relationship between the feedback resistor RF and the input resistors RA, RB and RC. The circuit can be used as either a summing amplifier, scaling amplifier or averaging amplifier. At node V2, IA plus IB plus IC equal to IB plus IF. Since RI and A of the operational amplifier are ideally infinity, therefore IB equal to 0 ampere, V1 equal to V2 approximately equal to 0 volt. Therefore, we can write VA by RA plus VB by RB plus VC by RC equal to minus V0 by RF. So from this, V0 can be written as V0 equal to minus of RF by RA into VA plus RF by RB into VB plus RF by RC into VC. Summer, also known as summing amplifier. The summing amplifier circuit shown in figure is simply a direct coupled inverting amplifier with two inputs applied to two resistors R1 and R2. An op-amp summing amplifier, it amplifies the sum of two or more input voltages. So summer or summing amplifier. Here the input currents are I1 equal to VI1 by R1, I2 equal to VI2 by R2. All of I1 and I2 flows through resistor R3, giving V0 equal to minus of I1 plus I2 into R3. Now substitute I1, I2 here. V0 equal to VI1 by R1 plus VI2 by R2 into R3. With R1 equal to R2, V0 equal to minus R3 divided by R1 into VI1 plus VI2. When all the three resistors are equal, when R3 equal to R1 equal to R2, the output voltage is the direct but inverted sum of the two inputs. Next, subtractor. The basic operational amplifier can be used as a subtractor as shown in this diagram. To analyze the operation of the circuit, assume that all resistors are of equal value. That is R1 equal to R2 equal to R3 equal to RF equal to R. The output voltage can be determined by using the superposition principle. If V1 equal to 0, that is V1 is grounded, then the output voltage V02 will be due to the input voltage V2 alone. Hence, the circuit shown becomes a non-inverting amplifier of unity gain with the input voltage V2 by 2 at the non-inverting input terminal, and the output voltage is given by V02 equal to V2 by 2 into 1 plus R by R. So that is equal to V2. Similarly, if V2 equal to 0, then the output voltage V01 will be due to V1 alone. Hence, the circuit becomes an inverting amplifier of unity gain, and the output voltage is given by V01 equal to minus V1. Now, considering that both the inputs are applied, the output voltage V0 is V0 equal to V02 plus V01. So, if you substitute that, V0 equal to V2 minus V1. Next, we have a differentiator. Differentiator, the figure shows a circuit of a differentiator. So this is the schematic representation of a differentiating circuit using operational amplifier. Note that the output is proportional to the differential of the input voltage. Applying nodal equation at terminal 1, we have C d by dt of V0 minus Vi, that is equal to 1 by R into Vi minus V0. But Vi equal to V0 by AV, and neglecting the small terms, we get V0 of t equal to minus RC d by dt of V of t. Hence, the output voltage is proportional to the differential of the input voltage. If the input voltage is sinusoidal, V of t equal to sin omega t, then the output voltage be V0 of t equal to minus RC omega cos omega t. And final application, integrator. A schematic representation of an integrator using op amp is shown in the following diagram. So this is the integrator circuit. So we have a capacitor in the feedback path. Since I equal to I dash, we have V minus Vi divided by R equal to C d by dt of Vi minus V0. Now Vi equal to V0 by AV, substitute this. Therefore, minus C d by dt of V0 minus V0 by AV equal to V by R minus V0 by AV R. Since AV is far greater than 1, V0 also far greater than V0 by AV. So we get C V0 of D equal to, so what we do is we integrate on both sides. After applying these simplifications, we integrate both sides of this equation. So C V0 of t equal to minus 1 by R interval 0 to t V of t dt plus 1 by AVR interval 0 to t V0 of t into dt, or V0 of t equal to minus 1 by RC integral 0 to t V of t dt plus 1 by RC AV integral 0 to t V0 of t dt. For a finite integration time and for large value of AV, the second term on the right hand in the above equation may be neglected in comparison with V0 of t. Thus, output V0 of t equal to minus 1 by RC integral 0 to t V of t dt. The amplifier therefore provides an output voltage proportional to the integral of the input voltage. Thus, it acts as an integrator.